So this might be the most powerful module of them all because we see it's the flashiest of dual-pol signatures. It's the one people like to catch on the most or spot the most or tweet the most or share the most because it involves an actual live tornado, the tornadic debris signature. But with great power to identify the presence of a tornado comes great responsibility. This signature, more than any other, you want to use wisely. You want to know what you're dealing with. You want to make sure that you are dealing with a tornadic debris signature and not something else. So I'm going to show you how to do that and the best way to use it wisely. But right on the edge, frequently, you have low reflectivity in that inflow region, so it might be very close to where your tornado is located. And that can be lots of things. Bugs, dust, they all drive CC down too, but you don't want to say you have a tornado present if you're just looking at dust and inflow into a storm. And so we want to be cautious about where we're diagnosing our TDS. So we're going to have some deep thoughts here for a second. If I want high correlation coefficient to trust data, we've shown all these examples previously. I want to trust the data. I want correlation coefficient high. Well, how do I trust a signature if the whole point of the signature is to have low correlation coefficient? Sort of this catch-22 here. So we're going to show you how to do that and how to make sure you can trust the signature when the signature actually involves low correlation coefficient. So we're going back to that example from Dallas-Fort Worth from the previous presentation of our ZDR arcs where we're looking at reflectivity at the lowest levels here. There is our velocity signature where we're starting to see something closer to rotation, but we see sort of a speckly image in velocity there. There's some noise in our velocity. Maybe we're not looking for, or we don't have just a very tight velocity couplet just yet, when in reality, we want to be looking for a nice tight couplet and cleaner velocity to associate with the tornadic debris signature. And we also want to know how high is the reflectivity in our area of question. This is sort of our area of question, and we'll overlay reflectivity again from our previous example. And so this is about where it lined up with our velocity. Here's our inflow. Our outbound winds with the radar to the northwest is in this direction on the rear flank of the storm. So this is sort of our area that we're curious about. We're going to go to correlation coefficient now. And we want to see low correlation coefficient, as we mentioned, at least less than about 0.9. And we want it very close to our velocity couplet. We want those to match up nicely. And we want it to overlap reflectivity of about, and these are sort of soft areas. It's a little bit of a gray area. It's not like at a defined threshold. You just want to put the puzzle pieces together to keep adding your confidence in the signature. But generally, you want about 20 dBz or higher. So we're going to outline our area where we have this really low correlation coefficient, where we're dealing with things we know is not meteorological, but what's causing the non-meteorological scatters. So we bring back sort of this transparent image of our reflectivity, and look at how it's overlapping there. It's kind of right on the edge. That's interesting. Nothing really overlaps, though, our higher reflectivity values. So in reality, we're just looking in this area, bugs, dust, things that are getting sucked into the updraft. So this is an oversized bug. That'd actually be scary if that were the size of the bug in real life relative to our inflow region we're looking at with the radar image here. But the whole point is that these aren't the scatterers you're looking for. Hopefully somebody got that reference in here. But we'll move forward as I make a fool of myself out here with these jokes. And as reflectivity continues to develop, we're going to look at velocity now going forward in time. Do we have that tight couplet, that clean velocity? Well, we see what looks much cleaner than the previous example and much tighter. We'll highlight it right there, so put a check mark next to that. How high is our reflectivity in the area of question? So let's overlay that. We go back and forth. That overlays quite nicely. That couplet's right in an area where we have reflectivity 30, 40, 50 dBz. That looks good too, so we'll give it a check mark. Let's go forward now to correlation coefficient. So we want that low CC, less than about 0.9, very close to the couplet. We overlay what we had from our velocity data previously. So we'll look right there. That looks pretty good to us. That's right in line with where we would, were at least the two matching up in terms of the radar range bins. So we'll give that a check mark. And again, we want it to overlap reflectivity at least about 20 dBz. We'll do that. So we put it over the top. Yeah, that looks pretty good to us too. So we're going to check that off. So we're starting to get more and more confidence here. That looks like perhaps a tornadic debris signature. And we circle it. And we'll go forward. Now, this is something that's interesting. You can use ZDR actually to add even more confidence to the potential for a tornadic debris signature. Well, why does that work the way it does? Well, if you have ZDR close to 0 dB, that can add confidence. And the reason why is if you get debris, perhaps these dancing, spiraling leaves that are present, things that are tumbling, debris that's tumbling, it's chaotic. There's no rhyme or reason really to it. While you can maybe get some things to start to align, frequently all this tumbling, it sends back equal amounts of power in the horizontal and the vertical. That gives you, remember, close to 0 dB in ZDR. So that even is another check mark that we have what looks to be debris as we zoom in and see those sort of grays and blues. That's that low ZDR close to 0 dB. But I will stress, it's not a necessity. The reason why we save ZDR for sort of the last part is if you start to mix in things like raindrops into your tornadic circulation, you get some of those big raindrops that have high ZDR because of the oblate nature to the raindrops. That can drive ZDR back upwards. You can see some of our examples here if you start to mix it in. And you can have ZDR values that are maybe 1, 2, even higher dB within your, the area of interest for your tornado. So low ZDR near 0 helps add confidence, but it's not a necessity for the tornadic debris signature. So you want to radar operate like a champion. How do we do that? Well, we want to make sure we're looking at the same range bins between variables. Something that can happen frequently, especially if we get different variables in at different times through whatever radar program you may be using. If there's a mismatch in our data, and you may think, oh, I got a TDS right, there's a huge TDS, but right here maybe isn't overlapping perfectly where we have high reflectivity. So you always want to be checking, going back and forth, making sure that it overlaps. And you want to make sure you got the same timestamps on all of your products to make sure you're looking at it at the same time, as different things may come in at different times, especially when you're looking at velocity versus reflectivity or some of the dual-pol data, just in the way the Weather Service radars do their scanning strategies. So the tornadic debris signature, it can serve as clear proof, if you identify it properly, that there was at least a recent or even ongoing tornado. You're seeing the tornadic debris. You want to see that tight velocity couplet and adjacent radar bins of the following. You want reflectivity again. These aren't hard and fast rules. There's a little bit of gray area, but generally greater than about 20 dBz with reflectivity. Correlation coefficient, generally less than about 0.9. And some of your big monster tornadoes, you start to get into your SIG-TORs, your violent TORs, generally will send correlation coefficient even farther down, closer to 0.6, 0.5 even, as you get tons of non-meteorological scatters in the debris field. ZDR, I highlight in yellow here. It can be very low, and that gives you added confidence, but the reason why I highlight it in yellow is it's not a necessity to be close to 0 dB. And you have to have that low correlation coefficient and sufficient reflectivity overlap. It can't say, well, it's close. It's kind of in the inflow area. It's right next to it. Yeah, sure. I want a tornado here. I'm going to check it off. That looks good to me. You can't do that. They got to overlap. You got to make sure you can trust the data. And considering that this signature gives you proof of the presence of a tornado, and it's one of the biggest hazards out there that we can forecast, you want to make sure you got it right. So you want to make sure those two overlap. And with that, we'll wrap up the tornadic debris signature.